Hey everyone, I'm QWebDev, and welcome to part 2 of the Domino computing series. In part 1, we've introduced domino logic gates and used them to build this 4-bit adder circuit that could calculate the sum of two numbers. Go watch part 1 if you haven't already. In this video, we'll improve the circuit with a cleaner design, better interface, and upgrade it to also support subtraction. We'll also take a look at more components and design concepts that'll be important to us later on. So without further ado, let's get to it. The first thing we can improve are the adder's inputs. At the moment, we have these designated input areas that represent the bits of each number, and we set values by adding or removing the dominoes in these spots. Now, for our specific use case, it works just fine, but generally it's not very ideal. If we ever need to connect another circuit to the adder, which by the way we're going to do in a moment, our input and output formats are not compatible. We need inputs that involve knocking over lines of dominoes, not placing them. Let's modify our inputs so that we can click on triggers to knock over the lines and set the appropriate bits. Not only is this more practical, but it also gives us a lot more freedom to organize the circuit. We no longer need each input to be right underneath its respective full adder. Now, this new input format does come with a small challenge. As you might know, humans can be kind of slow. So the person using this calculator should be allowed as much time as they need to enter the inputs. We don't want any calculations to begin until they hit the start trigger. When the triggers are hit and these lines start falling, they should not do anything prematurely. So what that means is we need some kind of quote-unquote domino memory. We need a circuit that can hold a falling domino line in place for an indefinite amount of time and later release it once it's needed by the adder. But how can we do that? Well, as a matter of fact, we've actually already looked at something that lets us do this. The domino AND gate. Let's take a look at our AND gate design again. First, we'll give the inputs more meaningful names than just input 1 and input 2. We'll call this input data and this one read. If we hit the data input, we've already seen what happens. The wave knocks out this domino and then stops. At this point in time, you can imagine that the AND gate is storing the information that the data input was hit. And no matter how long we wait without touching the circuit, that fact won't change. Then later on, if we want to retrieve that information, we can hit the read input. Since an AND gate requires both inputs to fall to produce an output, the output will be 1 if the data input was previously hit, and 0 if not. So in fact, a domino AND gate can act like a basic, single-use memory cell, which is exactly what we need. From here on out, I'll refer to this as AND memory. Anyway, this current AND gate design is kind of bulky, and there isn't always too much space to work with. So here's the more compact design that I'll be using. It might look a little daunting at a glance, but it functions the exact same way as the original AND gate, just optimized for size. Now, we can simply replace the original input spots with AND memory cells and connect them down to our new inputs. And just like that, we no longer have to worry about any premature calculations as we're entering the numbers. Hooray! Next, let's upgrade the circuit so that we can also choose to subtract two numbers. So we've already seen how to build an adder, now how do we build a subtractor? You might imagine that we need a second circuit that somehow does the opposite of what an adder does, but it's a lot easier. We can actually use our existing adder to subtract. But how do we do that? Well, think about it. How do you subtract using addition? Of course, we can make use of the fact that subtracting a number is the same as adding its negative. So if we had a way to negate a binary number, we can subtract our inputs by negating the second one before passing them to the adder. And since the negation is a lot simpler than full subtraction, this approach minimizes the amount of extra circuitry we need to build. But of course, the obvious next question is, how do we negate a binary number? How do we even represent negative numbers at all? There are a couple ways to go about this. First, let's try an intuitive approach by drawing some parallels from our regular number system. As you know, to negate something in decimal, we simply add or remove the minus sign in front of the number. We can translate this idea into binary by using the leftmost bit in a number to tell us whether or not it has a minus sign. This bit is called the sign bit. If the sign bit is 1, the number is negative, and if it's 0, it's positive. And of course, to negate a number, we just have to invert the sign bit. So far so good. This form is called sign magnitude representation, and it looks like a good solution at first, but its issues become clear once we actually try working with it. Let's try doing a problem, say 3 minus 5. 3 and 5 in binary are 0011 and 0101 respectively. 3 minus 5 is equivalent to 3 plus negative 5, so we'll negate 5 by inverting its sign bit, making it 1101. Now we can add these together as usual, and ignore this redundant overflow bit, which gives us our answer of 0? Huh? Yeah, clearly addition with sign magnitude numbers doesn't really work out. The problem is that the sign bit is no longer a place value. It's more of an arbitrary symbol that doesn't really represent a quantity. So adding the sign bits together isn't a meaningful operation. Imagine adding the minus signs of two numbers together in decimal. That just doesn't make sense. So we need a slightly different solution. We want to introduce a sign bit to allow for negative numbers, but we also want it to retain its quantitative nature to keep addition possible. A better approach is to instead negate the magnitude of the place value represented by the sign bit. So here, the sign bit, which is normally the 8th place, is now the negative 8th place. If this bit is 1, we subtract 8 from the total value of the number instead of add. For example, the number 1010 would be negative 6, because negative 8 plus 2 is negative 6. Since each bit still represents a quantity, addition should work just fine. But we can't test it just yet, because now we need to figure out how to negate numbers in this form. So how does negation work this time? Well, it's not as obvious as with sign magnitude numbers, so let's go step by step and derive the process using math. To start, let's have a look at the fundamental definition of negation. If we have some number x, then its negative, denoted by minus x, is defined as the value such that x plus negative x equals 0. We're going to manipulate this equation in order to get a non-trivial solution for negative x. We'll subtract 1 for both sides, and then move x to the right. Now let's try to simplify the right side. What is negative 1 minus x? Negative 1 in binary is just all 1s, because negative 8 plus 4 plus 2 plus 1 is negative 1. And let's subtract x, which we'll just denote with a bunch of x's. We might not know what the exact value of x is, but think about what happens here. Each bit in x that's 1 becomes a 0 in the answer, since 1 minus 1 is 0. And every 0 in x becomes a 1, because 1 minus 0 is 1. So when you subtract x from negative 1, the bits in x are simply inverted. And from this, we can conclude that negative 1 minus x is equal to not x, and this is our key discovery. Let's substitute this back into the equation, so now we have negative x minus 1 equals not x. We can isolate negative x by moving negative 1 to the right side, leaving us with our formula. Negative x equals not x plus 1. So to negate a number, we invert all of its bits and add 1. This process is called 2's complement, and it's exactly what electronic computers use because of how easy it is to operate with. Let's apply this to our previous example of 3 minus 5. To negate 5, we'll invert all of its bits, giving us 1010, and then add 1 to get 1011. Now we just add as usual, and we finally get our answer of negative 2. At last, we can rest easy knowing that negative numbers work out with addition. Alright, now that the concept is down, let's lay out the circuit. We need to negate the second input to do subtraction, so let's pass it through an inverter circuit that'll flip all of its bits. Next, we need to add 1. Now, we could build some additional logic that does this, but there's a better way. Remember that when we built the adder, we used full adders to calculate each place value except the 1s, because the 1s have no previous carry. But now we do have a previous carry, the plus 1 required for negation. So we're going to replace the half adder with a full adder and set its carry input to 1, which will add the extra 1 to the result. And this is the general design of our subtractor. But of course, we still want to be able to do addition, so we need a way to tell the circuit if we want to add or subtract the inputs. We'll do this with a third input that's just a single bit called operator. If this bit is 0, it signifies addition, and if it's 1, subtraction. We'll use this bit as a control line for the inverter, so that if we're subtracting, it'll invert the input, and if not, it'll leave it unchanged. So this actually needs to be a conditional inverter, controlled by the operator bit. we can also directly connect the operator bit to the carry input of the first full adder so that it adds 1 when we want to subtract. Finally, there's one more thing we're going to change about the circuit. Remember how this is a 4-bit adder? This allows for inputs from 0 to 15 and a sum from 0 to 30. But now that we're using 2's complement and negative numbers, half of the values we can represent have become negative. This shifts our ranges down to -8 to 7 for the inputs and -16 to 15 for the output. Even though these are still equally long ranges, they do feel more limiting. To keep our inputs within the original 0 to 15 range, we'll expand the circuit to make it a 5-bit adder. With 5-bit inputs, we can represent values from -16 to 15 and get a sum from -32 to 31. These new ranges fully contain our original ones, so we can leave our inputs as they are. Now, even though we can technically allow for negative inputs with this design, I'm not going to do that for the sake of consistency. So our inputs will stay between 0 and 15, and our output will range from -15 to 30 because of subtraction. Alright, with that out of the way, let's see how we can build this conditional inverter. As a quick summary, this component takes a 5-bit number and the operator bit as inputs. If the operator bit is 1, we want to invert the input, and if it's 0, we want to pass it through unchanged. So the question is, how do we invert a number only sometimes? Well, once again, we've already seen a component that does exactly this, the XOR gate. Let's take a look at the XOR truth table. The output is 1 when one or the other input is 1, but not neither or both. That might not sound very helpful, but here's another way you can think about it. Notice how when the first input is 0, the output is equal to the second input. And when the first input is 1, the output is the inverse of the second input. So in a way, you could say that one input is controlling whether or not the other should be inverted, and we can take advantage of that. If we XOR each input bit with the operator bit, that'll invert the input when the operator is 1 and leave it unchanged when it's 0. And to make timing easier, we'll use AND memory cells to hold the inputs in front of the XOR gates until it's time to use them. The memory cells will be read by the signal from the start trigger, which begins the calculation. This once again ensures that the circuit won't start before we finish entering the inputs. By the way, interpreting logic gates in unusual ways, whether it's AND gates as memory or XOR gates as inverters, is very useful knowledge and comes up pretty often when designing circuits. We've only looked at 2 examples so far, but there are plenty of other creative applications of circuits that go beyond their basic definitions. Can you think of any other examples? Why not leave a comment and let us know? Anyway, now that we have all the components ready, let's put this calculator together. First, we'll lay out the number inputs, and to the right of them will be the operator bit, followed by the start trigger, which begins the calculation. We'll connect the second input and the operator bit to the inverter on the right. The first input can be connected directly to the adder, and so can the output of the inverter. And finally, we'll connect the operator bit to the carry input of the first full adder, using one more AND memory cell to hold it in place. This memory cell will be read by, you guessed it, the start trigger. And here's our completed circuit. Beautiful, isn't it? Well, let's test it out. We'll use our previous example of 3 minus 5, so let's enter 0011 into the first input and 0101 into the second. And also remember to hit the operator bit for subtraction. Now we just hit the start trigger and we should get our answer of -2. Alright, here goes nothing. Cue even more overly intense music in 3, 2, 1,
go.
Alright, our answer is 111110, which is -2. And there we go. Here's our fully functional domino calculator that supports both addition and subtraction. Who needs a TI-84 when you have a TB63? Yeah. Well, that was fun, I guess. So where can we take it from here? If you ask me, the calculator's inputs and outputs could use some more work. I mean, think about it. All computers use binary, but the average person doesn't need to understand binary to use a computer. So in the next video, we'll address that and see what we can do to make things more user-friendly. Be sure to leave a like and subscribe so you don't miss that. As always, you can find the project files from my videos in my Discord server, link in the description. And if you'd like to support the channel in future videos, please consider becoming a member. You'll get a shout out in future videos, along with additional perks, and of course, it always means a lot to me. And with that, thanks for watching, and I'll see you next time.